We're Team 24051, and our project is hemp and cannabis biomass fiber extraction to make valuable bio-based raw materials.
I'm Josh, I'm the team lead, and I'm an industrial engineer.
I'm Travis, mechanical and procurement.
I'm Natalie, and I'm the biosystems engineer.
Hi, I'm Kai, I'm the chemical engineer.
My name's Emil, and I'm a mechanical engineer.
Hi, my name is Berge Design. I'm an industrial engineering student.
Hemp and cannabis growers face environmental, legal, and economic challenges when handling their plant waste. State regulations require destroying or transforming plant waste before its eventual shipment to a landfill, all at the expense and burden of the grower. Our sponsor, a startup company called Nexoterra, has a vision of aiding growers with these challenges while closing the loop within agricultural operations. Traditionally, cannabis is grown in order to harvest specific components like the flowers. However, there is hidden value within the stalk. Seen here, the stalk is composed of an outer layer of fibers called the bast and an inner woody core called the hurd. Bast can be transformed into sustainable bio-based products like fabric, insulation, cordage, or even hydroponic growing media, while the hurd can be used to make concrete, paper pulp, or even animal bedding. Following harvest, redding is the first step of the separation process that naturally occurs in the field as stalks rot and break down and the bonds between bast and hurd weaken. Redding naturally takes weeks to months but can be sped up through biological or chemical means. The next step of stalk separation is mechanical decortication, which was the primary focus of this project. Based on a traditional method with spinning rollers, this project required the creation of a small-scale machine, which can be deployed at growing facilities and providing growers a method to easily transform their own plant waste. Nexoterra would then come and collect the bast and hurd for their own bio-based product creation.
Before hemp is decorticated, it will likely be redded to assist in the breakdown of the stalks. A small set of tests were conducted to see if a novel method of soaking and microwaving stalks would be a viable alternative to the traditional redding methods. Hemp stalks were soaked at variable times between 12 and 36 hours, and then treated with microwaves depending on mass. The process did help with separation, but there was not a large difference between the treated and untreated stalks. It was concluded that it would likely be too labor-intensive at scale to compete with the traditional methods, and the benefits were not enough to justify its implementation.
Decortication is the mechanical stripping of the outer bast fiber from the hurdy core. By taking advantage of the brittle hurd and fiber's flexibility, rollers within the machine will deform and break the hurd while the bast fiber is stripped away. The decorticator is a standalone unit powered by 240 volts AC with a user-friendly analog control system and is no larger than the size of a standard washing machine for easy transport to remote greenhouses and farms.
The operation of the system is relatively simple, which can be seen in the system block diagram. The user interfaces with the electrical controls to start and stop the system, as well as adjust the speed. The user then takes pre-treated hemp stalks and feeds them through the rollers to create the end product of hurd and bast fiber.
In order to determine the required torque from the motor, we devised a testing apparatus that mimicked the full-scale machine, containing 2 sets of smooth rollers and a manual input. The deformation test performed with the same small-scale prototype helped determine the spring rate required for adequate destruction of the waste material, collect data on friction, deformation force, and ultimately torque. To determine the most effective grate spacing, a small-scale grate was reproduced, and pre-processed material obtained by our sponsor was used to carry out this test.
Our team also created a prototype for the machine's user controls and electrical system to allow for a smoother integration process later on. We wired our 3-phase motor to a variable frequency drive, or VFD, that converts from single-phase to 3-phase power. The VFD allows for versatility since it can be easily programmed through its own controls. There are many built-in features, but we utilized it for controlling the motor's start and halt, forward and reverse, speed control through an external potentiometer, emergency stop button, and signaling faults to the user. We also included a circuit breaker and solid-state relays that safely separate our system's high inputted voltage of 240 volts from the rest of the system through switching.
The frame is comprised fully of 14-gauge square steel tubing. The tubing was cut with cutting wheels on an angle grinder, then welded in 3 subsections and finally welded together with an arc welder. The frame stands about 4 feet tall and has holes and slots drilled in the 2 middle sections to fit the bearing and other hardware mounts.
Assembly of the machine required welding, drilling, a little bit of milling, and many fasteners. Each component is completely removable from the frame subassembly, and some of these components include the feed chute panels designed to protect the user from ejected material, reduce the risk of unintentional contact with the rollers, and plastic covers encasing the potentially hazardous mechanical drive system.
The following project requirements have been verified. Starting with roller performance, 90% of fibers must be longer than half an inch. Roller adjustment, the rollers shall adjust to varying stock diameters via spring mechanism. Throughput, the machine must be able to process 2 cubic feet per hour and 1 motor. The next is e-stop. The system shall provide an emergency stop option through a push button. Machinery cover, all mechanical components are separated from materials with covers. Following is the machine shall be corrosion resistant. In noise emission, the system operates at less than 105 dBA. We verified the following interface system requirements, including jam control, analog control usability, status light, operation verification, cable type, and electrical compatibility. And lastly, our design feature system requirements, including structural integrity, size, and accessibility. It is important to acknowledge that our grate separation system was unable to meet our requirement as the stalks did not properly distribute as they exited the decortication process. We will talk about our solution in the next steps. Although we were unable to overcome our separation challenges, our team was able to overcome a multitude of serious setbacks. Decortication is a relatively new industrial process, which means that there is minimal public information on the subject. Our team was able to successfully replicate this process with a less than $4,000 in total cost, something unheard of for this type of machine. Other challenges that we faced include a short fabrication timeline, procurement delays, and a lack of experience required us to be innovative in order to succeed. Our project consists of over 300 components and required substantial fabrication. Given the lack of experience building a project of this stature, our team should have ordered parts sooner and started building in order to anticipate long lead setbacks. Although our team struggled with finishing our project on time, our use of prototyping, specifically the electrical system, was the saving grace for completion. The most important component of our overall success was the team atmosphere that we worked in, as everyone understood the importance of working together. A project of this magnitude required all hands on deck, and our team delivered. Next steps for our machine include integrating a third set of rollers to further process the material, followed by extending the frame to allow the grate separator to process material in the same direction as the rollers, allowing for a streamlined flow. The addition of the 2 new rollers will also likely require a more robust motor to ensure that the stocks will be processed adequately. The roller design could also be reevaluated now that we have a functioning mechanical system to test different textures on the cylindrical surface. Here you can see our project poster, highlighted by our problem description, solution, methods, and results.
Moving to acknowledgement, we would like to acknowledge the support of Andrew Arias and Matt Christians, and the great Stadford, Mike Masons, and Nelly Bain.